Time, intangible, elusive time, measured in years by the broad movement of planets, measured in seconds by the inventions of man. Seconds, tiny fragments of time, marching single file down through the ages, writing the pages of history as they pass in review. 60 seconds every minute, 3,600 seconds every hour, 86,400 seconds every day. And with the fleeting life of each and every second, more than 6,000 gallons of oil are brought up from the earth. Oil from the east, oil from the west, the north, and the south, oil from 30 states of the USA, and from 50 countries of the world. Oil coming from the earth in huge quantities to fill our increasing demand. In the United States alone, enough oil is produced daily, in fact, to float a giant ocean vessel. And that's a job calling for a lot of manpower. For example, a famous football stadium seats over 100,000 persons. Yet 20 stadiums of this size can be filled to capacity by the number of persons steadily employed in the oil industry. Many men, many jobs, and all because less than 100 years ago, someone had an idea. An idea that perhaps a man could find oil in huge quantities by boring a hole into the earth. The idea of drilling specifically for oil was new, but the principle employed was an old one. Almost 3,000 years ago, the ancient Chinese had developed a laborious method of drilling for salt. The well drillers would jump on a springboard, something like a diving board. This would give slack to the rope supporting the drill tool, causing the tool to drop and pound into the earth. Out of this principle evolved the early method of drilling for oil, cable tool drilling, in which a walking beam took over the job of lifting and dropping the drill tool to pound a hole. Now, there are two common ways of forming a hole. One way is to pound or punch out a hole, as in cable tool drilling. The other way is to bore or scrape out a hole, and that's the idea behind modern rotary drilling. Using rotary drilling method, the search for oil has gone to almost unbelievable depth. The famed Empire State Building towers more than a quarter of a mile above the streets of New York. Yet its colossal height could be sunk into the depths of one of the world's deep oil wells. And another such building, and another, and another, and yet another, until 15 Empire State Buildings have been sunk to approach the depths which have been reached by rotary drilling. Suppose we watch the big job of sinking a deep well by the rotary method. The work begins with the erection of the derrick and the installation of the rig. This equipment may have cost up to $250,000, not to mention the $50,000 that may have been spent just getting into the well location. Before this exploratory well is completed, it may represent an investment of $1 million, and the chances of actually finding oil are about 1 in 9. With the derrick and rig installed, drilling operations get underway. We are making holes. A heavy steel rotable turns the drill string below ground. A square hollow pipe called the Kelly works off the rotary table, and fitting through a square hole is free to move up or down. Fitted to the Kelly is a length of drill pipe. More and more of these 30-foot sections are added as the well goes deeper. At the end of the drill pipe is a drill collar, and below this, the bit. There are more than 50 different... Here, a simple one is used to cut through the soft surface formation. Mud, scientifically treated mud, plays a highly important role in drilling operations. Circulated by a battery of powerful pumps, the mud is forced up into the swivel. Surging down through the hollow pipe of the drill string, it jets out around the bit to perform vital cooling and lubricating action. Returning up outside the drill pipe, the mud seals the walls of the well. This helps maintain pressure and prevents the walls from caving in. In addition, the mud carries up the drill cuttings from the bottom of the well, providing important information about the strata which is being penetrated. This is mud with a college education. Special chemicals and weighting materials are added from time to time to maintain the formula in precise balance. As drilling progresses, various types of underground formations are encountered. Now we're getting into hard stuff. We'll have to exchange our bit for one designed to penetrate this harder formation.
Let's pull her up.
This means pulling the string. A long job and one calling for precision teamwork between the members of the drilling crew and the ponderous equipment at their command. Section by section, the huge pipe is hauled up, carefully disjointed and stacked. 5 men working as one, handling tons of steel with a confidence born of long experience. And here's the new bit, designed for chewing through hard rock. This and many others will be worn out before the drilling is completed. After the new bit is in place, we'll have to recouple and lower the string again. With drilling underway once more, 3,000, 4,000, 5,000 feet down, the going gets tougher, slower. Hard rock and soft. Uh-oh, trouble. Yes, real trouble. A broken drill string. We'll have to quit drilling for the time being and go fishing. An attempt must be made to bring up the twist-off, or fish, from its position thousands of feet below. And here's the fishing tackle, a socket designed to slip over the broken end of the drill string with dogs to clutch it. It is lowered into the well on the drill string. The operation may take several days. Sometimes the fish refuses to be caught, even after every possible type of fishing tool has been used. With the fishing not making much headway, the engineers must decide whether to continue this costly operation, or to abandon the well, or to whipstock. The decision is whipstock. We'll try to go around the broken drill string by veering off from the straight hole. Yes, now we're doing exactly that by directional drilling. With a whipstock, a beveled piece of steel shaped to deflect our bit over at the precise angle desired, we are accomplishing the seemingly impossible feat of drilling a curved hole. We have angled our well over to bypass the broken string. And again, the drilling is continued, but now more cautiously than ever. We're down past the 10,000-foot mark and nearing the spot that our scientists tell us should be productive formation. Rate of penetration has increased. Soft formation and maybe, well, we've got to get a sample of what we're hitting down there. A special core-taking barrel is lowered into the drill string by means of a cable and windlass. The core barrel, held firmly within the drill collar, works like Grandma's cookie cutter. It slices out the desired core sample, which is retained within the barrel and hauled back to the surface on the cable. A careful analysis proves our core to be essentially water-bearing, despite minor oil stains. Not good enough for production. Disappointing, but maybe a little farther down. Another 300, 400 feet, and again, the speed of penetration picks up. This time, we'll use electric logging to see what we're getting into. This device consists of a group of electrical instruments which enable us to get an indication of the physical character and fluid content of the formation we have penetrated. The reading looks favorable. We'll case the formation off. A cementing outfit is called in. The cement is mixed on the spot and pumped to a special connection at the top of the casing. Forced down with mud, the cement rises between the casing and the wall of the well. The cement is allowed to harden. And now we are ready to cut loose the heavy artillery. A gun perforator is lowered into the well. The device is fired. Heavy caliber bullets pierce the steel casing and cement to let in the oil. Now tubing has been run into the well, and if she's going to produce, it'll come through that tubing. A Christmas tree has been added to control the expected flow. Oil or water is forced through the tubing to flush out the mud. Only about 1 out of 9 exploratory wells is productive. A few tense seconds, and we'll know about the one we've been working on for so many weeks. It's now or never. We've brought her in. It's the birth of an oil field.
and night we toil. Drill, men, drill, this is the song of oil. The drill goes down, and then the drill goes round. Plunk, hit, plunk, until the oil is found.
Yes, it's the birth of an oil field. One more victory in the ceaseless night and day job of searching, drilling, bringing up from the earth new supplies of petroleum to fill the increasing demands of modern living. We drilled a well and found some oil. Now begins the many-sided job of production, getting the oil out of the ground and into the refineries. To produce oil efficiently from this area, additional well locations must be scientifically plotted and drilled in. Roads must be built, equipment installed, oil storage and treatment facilities erected, pipelines laid. 1,001 tasks performed by men of almost every sort of skill and training. Perhaps you'd like to meet one of these oil men, a production engineer. His job is conservation, getting the last possible oil from nature's reservoir and getting it efficiently. Pardon me, Mr. Benson. Mind if we ask you a question?
Why, certainly not, but keep it simple, will you?
Well, this should be easy for you. When you drill in a well, what makes the oil flow to the surface?
Well, actually, some new wells never do flow. However, when an oil well does flow unaided, it's usually because of gas pressure, water pressure, or a combination of both. Take a look at that model, for instance. That's a simple anticlinal structure, an oil trap. The oil-bearing stratum is sandwiched between layers of impervious rock, which prevent the oil from escaping. Oil deposits, you know, occur in the pores of rock, not in underground pools or lakes. Usually there is water found in connection with oil deposits. Since oil is lighter than water, the two will be separated, the oil occurring above the water. Where there is oil, there is gas. Gas will always be found dissolved in the oil, and in some cases, additional gas will occur in a free state above the oil. So much for setting the stage. Now, suppose we sink a well and tap the oil sands. If the well flows, it means that some form of natural energy is working for us. Otherwise, we'd have to pump, right?
Right.
Okay. Now, in a flowing well, the main source of energy that lifts the oil is, in most cases, expanding gas. Now, the expanding gas, well, here, let's take this siphon bottle. Our flowing well is similar to the tube in the siphon bottle. It reaches into the oil zone, and when the valve is opened, the energy of the expanding gas raises both or mist or foam. Now, suppose we sink another well in a different location. Unfortunately, we've missed the oil zone. Well number 2 is like the shortened tube in the siphon bottle. It can produce only gas. Hence, we would leave it shut in. We want to conserve the gas energy for driving the oil up well number 1. As we continue to produce oil and gas from the well, the free gas has more room to expand. As a result, the gas pressure gradually declines. The well may flow for months or even years, but the decline in gas pressure is inevitable. Eventually, a point is reached where there is no longer sufficient pressure to force the oil to the surface. In this case, the well will have to be pumped. Now, we've been talking mainly about lifting oil to the surface. But remember, the oil must also be moved from various parts of the formation into the well. While gas plays an important part in bringing oil into the well, there is another force which in many fields is equally or more effective in this work. The driving force of encroaching water. This water exerts pressure from below, and as oil is produced at the surface, the incoming water replaces it. In time, however, the natural forces exerted by water or gas or both may become too weak to move the oil into the well at a sufficient rate.
Well, what do you do then?
Well, there are several methods of recovering a portion of the oil remaining in the formation. They involve what we call repressuring. In one method, enormous quantities of gas are pumped back into the formation. In this way, part of the original gas pressure can sometimes be restored, causing the wells to produce at a higher rate. In another method, Large volumes of water are pumped into certain wells. This creates an artificial water drive, forcing the oil to the other wells.
Well, I can see that there's more to this oil business than appears on the surface.
Oh, you're right about that. Now, let's step over here for a minute and we'll take a look out the window. There's a modern oil-producing field for you. The derricks have all been removed, farm crops growing nearby, and no sign of the wells except for a neat little Christmas tree. The Christmas tree is simply a group of valves and pressure gauges used to control the flow of oil and gas from the well. We try to conserve the natural gas pressures as long as possible by producing the most oil with the least amount of gas. Of course, day by day, the gas pressure declines, and eventually there won't be enough pressure to force the oil to the surface.
What do you do then?
The well must be pumped. There are many different types of oil pumps, but they all work on much the same principle. Like Grandma's old-fashioned cistern pump. Only Grandma had to use elbow grease to get the water out. Modern oil well pumps are usually driven by power plants which use natural gas from the fields or electricity. The power plant actuates a walking beam, which in turn imparts an up and down movement to a string of sucker rods. The sucker rods are connected to the pump at the bottom of the well. Simple valves open and close with the motion of the pump, raising the oil to the surface.
Boy, certainly takes a lot of equipment to produce oil.
Yes, and actually, you've seen only a small part of it. Well, what else can I do for you?
Got time to answer one more question?
Why, surely. What is it?
What do you do with the oil after you bring it to the surface?
In a word, we move it into the refineries. Here, take a look at this model setup. I think it'll help answer the question. This layout represents the whole business of oil production in a nutshell. Generally, the product of an oil well is a mixture of oil, gas, and water. This mixture flows first to a gas trap. The gas trap separates the so-called wet gas from the oil and water. Leaving the oil for a moment, let's follow the wet gas to an absorption plant. Here, the wet gas is literally dried by extracting liquid products such as natural gasoline, propane, butane, and isobutane. From the absorption plant, the dry gas goes to public utility companies, who in turn supply it to homes and industries for heat, power, and manufacturing processes. So much for the gas. Now let's go back to the gas separator and see what happens to the oil. After the wet gas has been removed, the oil usually flows to a dehydration plant or settling tank, which serves to remove water from the oil. The treatment and disposal of this unwelcome water is quite a story in itself. But let's follow the clean oil now to the field tanks. When these tanks are full, the quantity of oil in the tank is measured or gauged. At the same time, samples of the oil are taken from the tanks and sent to a laboratory, where tests are made to determine the quality and value of the oil. From the field tanks, the gauged and tested oil moves to a pumping station, where it is boosted along on the last stage of its journey to the refineries. And that's where our job of production ends, and the complex job of refining the crude oil into marketable products begins.
Many men, many jobs, and all because someone had an idea. An idea that expanded into a major industry, transforming vast areas of worthless land into gainful property, benefiting thousands of private landowners through the monthly payment of royalties, giving birth and sustenance to hundreds of clean, orderly communities around oil-producing and refining centers, and developing a multitude of products which contribute so much to man's comfort in terms of heat, power, freedom of movement, and physical well-being. Only time and continuing research on the part of the petroleum industry will reveal what added comforts may be developed for the generations of today and the generations of the days to come.